Okay, ladies and gentlemen, we started with the field effect transistors section 8.3 JFET biasing in the previous lesson, and we did the cell biasing. Today we're going to carry on doing the voltage divider bias and the current source bias. Alright, if we refer to our textbooks, voltage divider bias on page 387. An N-channel JFET with voltage divider bias is shown in figure 823. The voltage at the source of the JFET must be more positive than the voltage at the gate in order to keep the gate source junction reverse biased. Remember, we had the same with the cell biasing. That is, of course, the rule using a JFET that the gate source junction should be reverse biased. This circuit should look familiar to you. We have discussed the BJT extensively using the voltage divider bias as well. Here you can see I've got my voltage divider using R1 and R2, and of course still this junction between the gate and the source should be reverse biased. Alright, so let's have a look at the formulas. You should recognize them because they're basically the same as the BJT, only of course that we are talking about the drain, gate and source and not the collector, base and emitter as in the BJT. Alright, then the source voltage Vs is ID over Rs, and then the gate voltage is set by the resistors R1 and R2 is expressed in the following equation, voltage divider formula, and you can see exactly the same as for the BJT, only now it's not VB but VG, R2 divided by R1 plus R2 times VDD, and not VCC as in the BJT. Gate to source voltage VGS, VG minus VS. Source voltage Vs is equal to Vg minus Vs, all boiling down to Kirchhoff's laws and Ohm's laws again. Drain current ID is equal to Vs over Rs on the next page, and then substituting using Kirchhoff's law and Ohm's law simultaneously, ID is equal to Vg minus Vgs over Rs. But let's have a look at the example there quickly. Example 8.11. Determine ID and VGS for the JFET with a voltage divider bias in figure 824, given that for this particular JFET the parameter values are such that VD is equal to 7 volts. Alright, we look at the solution. ID then, just using the formula, ID VDD over VDD minus VD over RD, I get a current of 1.52 milliamps. I can just stress again, remember that calculations in this textbook is not accurate to 3 decimals. You have to do it accurately to 3 decimals and express your answers in engineering notation. Then I can calculate the gate to source voltage. Vs is equal to IDRS, 3.34 volts. Vg using the voltage divider formula, 1.54 volts. Then VGS is Vg minus Vs, and I see I get my negative voltage as it should be for reverse biasing between the gate and the source, minus 1.8 volts. Please take note on that example. If Vd had not been given in this example, the Q point values could not have been found without the transfer characteristic curve, of course. Alright, also very important, and please pay attention in this section, the graphical analysis of a JFET with voltage divider bias. You can mark, as I've done as well. An approach similar to the one used for the cell bias can be used with voltage divider bias to graphically determine the Q point of a circuit on the transfer characteristic curve. In a JFET with voltage divider bias, when ID is equal to 0, VGS is not 0. Please underline that. Remember, we had with this cell biasing, when ID was equal to 0, VGS was also equal to 0, and my load lines first point, the point of origin, started at 0 point. And I can see in the case of the voltage divider bias JFET, that is not the case. Alright, as you can see there in your textbooks as well, it says there, because the voltage divider produces a voltage at the gate independent of the drain current. Independent of the drain current. When we look at the formulas there, so for ID, when ID is equal to 0, Vs is equal to IDRS, which will give me 0, but VGS, which is Vg minus Vs, is Vg minus 0. So it's going to be equal to Vg. Alright, and I can see it here on the curve for the voltage divider bias. So you can see there's my first point that I can plot on my curve. Let's try again. Alright, so not at the origin like for the cell biasing. Please take note of that. Don't make that mistake. Alright, then of course I have to calculate the second point so that I can draw the load line. How is that done? It carries on there on the next page. When VGS is equal to 0, remember the first, with the cell biasing, it was when ID is equal to 0, and when the second point was calculated when ID was equal to IDSS. In this case it was where ID is equal to 0, but the second point is where VGS is equal to 0. So for VGS is equal to 0, I calculate the value of ID, which is VG minus VGS over RS, which boils down to VG over RS, because VGS is equal to 0. I assume it to be 0. Then the second point on the line is at ID, which is equal to VG over RS, and VG is equal to 0. So here's VG is equal to 0. Then I calculated this point. That's my second point. VG over RS for the voltage divider, ne? Sorry, there it is. Second point over there, where VGS is equal to 0, I calculated the value of ID. So that's my second point. And now you can already see what happens. I draw my load line, connect these 2 points, but I extend the load line. That's why you have to have a ruler until it cuts my curve, and you will write there for me, that's my Q point. That's my Q point. Alright, so please take note of the difference between the cell bias and the voltage divider bias load line. Anyway, I made an example again because I told you I'm very good with Photoshop. So I swapped it around. Of course, for the P channel it would look this way, ne? So make sure VGS off for a P channel now is positive. So my characteristic curve will lie on the right hand side of the ID axis. Okay. So let's have a look at an example. Example 8.12. Determine the approximate Q point for the JFET with the voltage divider bias in figure 826A, given that this particular device has a transfer characteristic curve as shown. Remember again, if I don't give you the transfer characteristic curve, again you can draw it. You must have the, however, IDSS and VGS off, then you can draw it by calculating values for ID in steps of 1 volt for VGS. Alright, so once I've got that, then I must go and do my calculations, of course. So if you look at the example, page 390, we've seen what we've discussed. First, establish the 2 points. Firstly, it was when ID is equal to 0. Then we've seen, of course, VGS is not equal to 0. Alright, so in this case 4 volts. So there's my first point. 4 volts calculated where ID is equal to 0. That's the value of VGS at 4 volts. So I have to calculate the second point where VGS is equal to 0, then I will calculate the value of ID, which is VG over RS, and I get a value of 1,2 milliamps, and I plot my second point there. Alright, so then you can see I connect the two, and I extend the load line, and you will write there, that is my Q point. And then what you're going to do further, because I only look at this, I don't look at your calculations, I want to see on this graph that you know what you're doing. Then you will draw a broken line to show me what is the parameters for the Q point for the values of ID and VGS. And I can see here, in this case, ID is equal to 1,8 milliamps and VGS is minus 1,8 volts. I just want to stress again, you have to include all the labeling. You have to name the axis and what the units are. ID in milliamps, VGS in volts. And where is VGS off? Where is IDSS? Especially if you plotted the curve yourself. And then plot the curve and do your calculations and draw the load line. Show me where the Q point is. Write in the values. And ladies and gentlemen, please make sure that you have a look at the scale that has been used. We can see in this case, IDSS is 12 milliamps. So each block, if you go and count them, is going to be equal to 1 milliamp. But look at the voltage. Can you see VGS off is minus 3. So it's not one block that's been used. So it's 2 blocks for each voltage. Né? So you make sure that you have a look, or even make sure that you choose a correct scale so that you can write the correct values down. Alright, that is the graphical analysis of a voltage divider, bias JFET. Before we carry on, we want to look at the Q point stability for the JFET. Remember, that was also quite a factor that we had to discuss or discussed in for the BJT. Unfortunately, for the transfer characteristic of a JFET can differ considerably from one device to another of the same type. Same problem we had with the BJT. If, for example, a 2N5459 JFET is replaced in a given bias circuit with another, the transfer characteristic curve can vary greatly, as illustrated in figure 8.27a. In this case, the maximum IDSS is 16 milliamps. There you can see. Can vary from there to there by just changing. This is for the cell biasing. You can see it's a cell biased, especially if I go and look at figure B where the load line is drawn, and I can see that the load line starts at the origin of the curve 0, 0. Né? Alright, so a large difference of IDs for a specific device. I think you can remember from the data sheet, it was given us a minimum value, a typical value, and a maximum value, so there was quite a large range. So I can see it's not very stable. When I go and compare it to the voltage dividers, as on page 391, it says there, if a self-biased DC load is drawn as illustrated in figure 827b, the same circuit using a 2N5459 can have a Q point anywhere along the line from Q1, the minimum bias point, to Q2, the maximum bias point. Accordingly, the drain current can be any value between ID1 and ID2 as shown by the shaded area. This means that the DC voltage at the drain can have a range of values depending on ID. Also, the gate to source voltage can be any value between VGS1 and VGS2 as indicated. That was actually the previous figure that we looked at. Alright, but the comparison You can see here with the comparison between the two. Comparison here between the two. Figure 28 illustrates the Q point stability for a cell bias JFET and for a JFET with a voltage divider bias. With voltage divider bias, the dependency of ID on the range of Q points is reduced because of the slope of the load line that is less for a cell bias for a given JFET. Although VGS varies quite a bit for both cell bias and voltage divider bias, ID is much more stable with a voltage divider bias, and we can see it here in this figure. You can see this range here on the cell bias is much larger than it is here for the voltage divider bias. So again, the voltage divider bias more stable than the self-biased JFET. Alright, the last one that I want to discuss with you is the current source bias on page 391. Current source bias. The current source bias is a method for increasing the Q point stability of a self-biased JFET by making the drain current essentially independent of VGS. This is accomplished by using a constant current source in series with a JFET source as shown in figure 829A. 829A, we can see there's my constant current source. In this case, it has been done with a BJT. Let's see what happens. In this circuit, a BJT acts as the constant current source because its emitter current is essentially constant if VEE is much bigger than VBE, which it normally is. A field effect transistor can also be used as a constant current source. So if we look at the formulas there, you can see the IE is equal to VEE minus VBE over RE, and of course if VEE is much larger, then I can say it's only VEE over RE. So since IE is equal to ID or equivalent to ID, ID is equal to VEE over RE. So as you can see in figure 829B, ID remains constant for any transfer characteristic curve as indicated by the horizontal line. So I can see here that this circuit with a constant current source gives me a very stable transfer characteristic. Alright, then an example 813 on page 392. Just doing some calculations to calculate the resistor values. A current source bias circuit, like in figure 829, has the following values. VDD 9 volts, VEE is equal to minus 6 volts, and RG is equal to 10 mega ohms. Remember, we talked earlier about this value of RG, and we said we choose a large value, normally in the range of 10 mega ohms. To produce a 10 milliamp drain current and a 5 volt drain voltage, determine the values for RE and RD. So just use my formulas. RE is equal to VEE over ID, value of 600 ohms, RD, VDD minus VD over ID, value of 400 ohms. Alright, so those are the three biasing methods that we will discuss for the voltage, for the JFET. It's the cell bias, the voltage divider bias, and the constant current source biasing. So what you need to go and do now, of course, is to read through the sections discussed, work through the examples, again do the true false quiz, circuit action quiz self-tests, and do the relevant basic problems to this section, which is now 16 to 27. So this concludes then section 8.3.